consolidating this information. The dependent variable is the difference, and then you're only using the baseline here. So it's only one if you have 100 observations. 100 units, you have 100 observations in your data set, even though you may have collected 200 observations. And unlike the other models, it's like only the dependent variable is using the longitudinality of the sample. You're only differencing out in the dependent variable. All these other, the rest of the regression is essentially cross-sectional. So as a result, what you're controlling for then are the baseline differences, but you're not controlling for any time-varying characteristics in your sample. So it's a perfectly good approach, but it's not a full panel model at all. You're not doing anything. You're controlling for observable time-varying characteristics by sticking them in Z, but you can do that in a cross-sectional context. That effectively is a cross-sectional context. You're saying, how does the level of my observation, of my independent variable, affect the change, the difference, the change in my dependent variable? Compare that to the first differences model. Again, same panel data setup. But now we're estimating the change in Y as a function of the change in the time-invariant things and the change in the treatment status. The Z, the time-invariant characteristics, by construction fall out, and they fall out, even though I didn't write it, they fall out both of the observable and, because we're first differencing, out of the unobservable set. So by doing the differencing, again, we're controlling for everything that's time-invariant. Anything that is time-invariant will fall out of the model. So that's using the panelness, the longitudinality of the sample on both the dependent side and the independent side. And the bonus of that is that we're getting control for everything that's time-invariant. Change score doesn't do that. Take the change score and turn it into a first differences model, and it gets done. We're not controlling for unobservable time varying characteristics. We're only controlling for observable time varying characteristics. That is, the x's that we can see that change over time, we can't control for. Panel data does not get you around unobservable time varying variables, just like difference in differences. If you saw a policy, exactly the same thing. In 1991, a policy occurred in New York regarding cabbage surgery. We can look pre to post, we can use control groups and so on and so forth. We cannot rule out that there was something else that also occurred in 1991 that influenced how surgeons select cabbage patients, that influenced their racial differences. The more differencing we do, the less likely it is that we'll have something else that affects that particular set of things in that particular way. But we can never rule it out. We have to make assumptions about it if we want to say something about causality. So the important thing here again is panel data, not a panacea. Not a panacea, but gets you that extra action on unobservables that are time invariant. What about the lag dependent variable model? Same setup as again. Now we're modeling the second period outcome as a function of all the same stuff as the change score model, but where we had yi2 minus yi1, we've moved it over into being a covariate. We're saying what's the level, instead of what's the change, we're saying what's the level in the second period as a function of all the same stuff and the level in the first period. Again, we're controlling for baseline observables, and it is a lot like the change score, but it turns out that there are some reasons, if you see this article by Vickers and Altman and BMJ, there's some reasons they argue to prefer the lag dependent variable in the context rather than a change score model, because you're explicitly controlling for baseline differences in this value in a way that you're not necessarily doing so in the change score model. But the other thing that's useful about the lag dependent variable is that it extends more readily to a multi-time period setup, whereas the change score, well, the change score you can do in a multi-time period setup as well, but it doesn't make as much sense. So here you're saying rather than this phenomenon, this outcome being really a function of, or the things that really matter about this outcome are the time invariant stuff, you might say that in addition to the observables, what we really care about is this sort of state dependent where you are in the previous period. And if we have time on Thursday, I'll try to show you some of this. You can think about extending this model to say, okay, I now controlled for your time period. Like, your drug-eluting stent use is a function of your drug-eluting stent now is a function of your drug-eluting stent use last year. It might be that you can add multiple lag variables. So it's not only how important you were last year, but it's also the year before that, the year before that. Depending on the data, you can then lag backwards and control for this longitudinal history of your phenomenon in a way that doesn't make any sense at all in a simple change score setup. That was kind of a little bit of deviation, but that's what you get. All right, so it's we're out of time. I do want to go over some actual code examples, but I think we'll have to save them for Thursday. Okay, yeah. All right, any questions before we call it a day? Good. All right, well, wake up and enjoy lunch.
Yeah.
Knock off.
What do you think?